All right, everybody, welcome to Math with Grace. Today we're going to be working through Pre-Calculus, Unit 6, Section 2. Section 2 begins on page 27 and it's titled Vectors. There is a bunch of vocabulary here that is pretty important to understand and know, but most of the lesson starts on the next page, so we're going to go ahead and turn the page here and get jumping right in. Scalars and vectors, okay, is what we have here. It says not all quantities can be expressed simply by a magnitude. Direction on how to get somewhere require that you know both how far, which is the magnitude, and what direction, okay? Scalar quantities are quantities that can be expressed by specifying a certain number of units. All right. Vectors are quantities that have both magnitude and direction. Vector, okay, with both magnitude and direction. A vector is represented by an arrow that points in the direction of movement. The endpoint is referred to as the tail, and the arrow is called the head or the tip. Okay, tail, tip, tail or head, right? The arrow points in the direction of the movement. Typically, vectors are noted with a bold letter or by putting an arrow above a line or below the letters used to name the vector. The notation for the magnitude of a vector is these absolute value marks, right? For vector v, the magnitude is represented as the absolute value of v. I don't know how to say that, the magnitude of vector v, okay? So a unit vector, it says if the magnitude of vector v is equal to 1, then the vector v is a unit vector. Any force has both magnitude and direction, so a force is represented by a vector. Okay, so they have an illustration here in the second column of a couple of forces, okay, with a direction, all right? You can see here that it is a B with an arrow over it, although it only has one. It looks like this. I mean, it's very small, but it looks like that. So, key point to note here, it says that the vector is named in the same way a ray is named. The name begins with the tail, right? So AB, A is the tail, B is the head. So we name it AB, all right? That also helps us when we're looking at illustrations to know which direction it's going, right? It's going from A to B. It's moving that way. Vectors may be added geometrically by head to tail method. The sum is found by placing the head of one vector to the tail of another and then connecting the tail to the first vector or to the tip of the second. The resultant is a diagonal of the parallelogram formed by the vector. So the resultant is the sum of our vectors, okay? This same parallelogram is formed if the vectors are placed tail to tail. So here is tail, head, right? And this one goes this way, tail, head, right? If you put it the other way, it matches up just the same, okay? The resultant is the same. It's the diagonal portion, all right? A key point here, vectors can only be added to each other. Scalars and vectors cannot be added. They are not like numbers, okay? Says we're talking about a lot of stuff here, but we will do some examples. We'll get to them. I know this is a lot of information. Don't stress. The problems aren't as bad as they seem. Since force is a vector, the result of two or more forces acting on an object can be represented as the sum of the vectors. The resultant will produce the same effect on the object as the joint action of two or more forces. So, in this drawing here, this is force sub 2, right? It's pulling this way. Force sub 1 is pulling this way. If we were to add them together and get the resultant would be this, and it'd be pulling this direction, but it would apply the same amount of force that those two things are doing at the same time, okay? The resultant force is referred to as the parallelogram of forces. It says you should be familiar with the following facts about parallelograms before we continue, okay? Both pairs of opposite sides are parallel and congruent. This side is equal to this side and parallel to, they're parallel to each other. This side is equal to this side and they are parallel to each other. That's what makes it a parallelogram. Opposite angles are congruent. This angle here is equal to this angle here. This large angle is equal to this large angle, okay? Consecutive angles are supplementary. Angle C is supplementary to CBA, this whole big thing. Just like angle C is supplementary to COA, this whole thing here, all right? Diagonal divides the parallelogram into two congruent triangles. So this is divided into two congruent triangles, but when we divide a parallelogram, the triangles, this can't just be folded in half and have those triangles match up. They're not congruent in that way, okay? OBC, this angle for this triangle here, OBC is congruent to BOA. Okay, these two angles are congruent to each other. All right, this angle is congruent to this angle. Remember, there's corresponding parts that have to match up. So it's not a simple, this is equal to this. That is not a true statement, okay? So we need to be careful how we're looking at those triangles, all right? Another thing to review here in this next column on page 29 is the formulas for working with right triangles, right? The sine is opposite over hypotenuse. The cosine is adjacent over hypotenuse, and the tangent is opposite over adjacent. Let's take a look here at our first example. Two forces, one of 60 pounds and the other of 80 pounds, act at a point on a body at right angles to each other. So this is a right angle, okay, which means this is a right angle, that's a right angle, and that's a right angle. What single force would have the same effect on the body? Adding these up, what would it be? Well, this side they've labeled with the 60, and this side they label with the 80. If this is 60, then this is 60. If this is 80, then this is 80. If this is a right angle where they act on each other, so is this. And so by doing that, I'm going to draw it off to the side here, so it's kind of separate. We have a right angle that looks similar to this, with 60 on this side and an 80 on this side. Basically, they want to know what is the hypotenuse of this triangle. And right here, they're doing it, right? They are doing the Pythagorean theorem to solve for R being 100 pounds. 100 pounds of force being pulled in this direction. Now, the question is, what direction is that? Here's where our sine, cosine, tangent come in, okay? We need to figure out what this angle is, okay? Nope, I'm sorry. That is not a true statement. We need to figure out, technically, this angle, okay? How far it's coming off of the horizontal force. What is this angle, okay? That will give us our direction. It says, since force is a vector, you must give its magnitude direction. Okay, the direction is going to be in degrees. Since we're looking for this angle, remember when we were talking about congruent triangles, it's the same as this. So we need to solve for this. Now we have to do it with a tangent because we don't have the hypotenuse. Well, we do, but we were given this other data, so we should use the data we were given just in case our answer is not correct, right? So the tangent of this angle is the opposite, which is 60, okay, over the adjacent, which is 80. They made that into a fraction and then took the inverse, the tangent to the -1, right, and got that it's a 37 degree. So the resulting force has a magnitude of 100 pounds at an angle of 37 degrees with the horizontal, okay, with the horizontal. So up from the horizontal, this is 37 degrees. All right, and we could figure out the rest fairly easily if we were asked to do so. All right, so that's our first example. So a lot of words that we went through, a lot of vocabulary really, but this not so bad, right? All right, let's turn the page. All right, so here we are on page 30. It says the following formulas are for working with oblique triangles. Remember, we just learned those in the last sections, the law of sines, the law of cosines. Now, they didn't write out all of the different variations of the law of cosine, but that's all right because we got that under our belt, right? So let's take a look at this next example. A box is being pulled by 2 ropes with forces of 3 and 4 newtons at an angle of 40 degrees with each other. So 40 degrees with each other means it's this whole angle is 40 degrees, okay? What is the magnitude of the resultant force on the box? What is the red line? Now for this, we have 2 sides in the included angle, right? But really, that only helps us if we were looking for this diagonal. But we aren't looking for that diagonal, right? So we have to do a little bit more work. Now, if this is 3, then this is 3. If this is 4, then this is 4, right? We know that about triangles. Or not triangles, sorry, parallelograms. Now, if this is 40, angle A is supplementary to that, meaning together they equal 180 degrees. So if we take 180 degrees and subtract 40, we figure out that this angle is 140 degrees. Now we have 2 sides and an included angle for the diagonal that we actually want to solve for. Okay, that's what we needed. So we can use the law of cosines. BD squared is going to be 3 squared plus 4 squared minus 2 times 3 times 4 times the cosine of 140 degrees, the included angle. They solve it and find that BD is 6.6. So the magnitude of the resulting force is 6.6 newtons. Okay, they're asking for the magnitude, not the direction and things. So we don't have to do anything else with that problem at this time. Looking at the next example. The resultant of 2 forces is 12 pounds. So now we know the diagonal part, right? The resultant makes an angle of 40 degrees with the 5-pound force. Okay, find the magnitude to the nearest tenth of the other force and the angle it makes with the resultant to the nearest degree. Okay, the solution for this is up at the top of the next column. I'm going to go ahead and draw it in, okay? So we have our parallelogram here. Kind of hard to draw on the crook of the book here. Our resultant is 12 pounds. So this is 12. And it says it makes a 40-degree angle with a 5-pound weight or force, okay? This one was 12 pounds. So what they're asking for is find the magnitude to the nearest tenth of the other force. So they want us to find this other force and the angle that it makes. So I'm just going to call those X and Y. All right. Now, to find the opposite force, we have to use the law of cosines because we know this side and its included angle. So what we'll be solving for is this, which I marked X here, but this is also X, right? If this is X, then this is X. They're both the same. So that's what we're solving for. X squared equals 5 squared plus 12 squared minus 2 times 5 times 12 times the cosine of 40 degrees. They solve and discover that X is equal to 8.8 pounds. So now we know that this is 8.8 pounds, right? Which means this is also 8.8 pounds right here. Okay, I'm going to erase my X and write 8.8 pounds, right? Now we can use the law of sines to solve for the angle measure because we know that this is 40. So 40, if this is 40, then this is 40, right? We've gone over that a lot. But 40 is to 8 pounds, 40 degrees. The sine of 40 degrees, is to 8 pounds as we're trying to solve for this one right here, right? Which is the same as that. The sine of theta is to 5 pounds. Then we solve, take the inverse, right? And we discover that it is 21 degrees. Okay, so we got to know and understand how to use our parallelograms. And then these problems are really kind of straightforward. I mean, there's multiple steps, but you know what? That's math, right? Next example. Find the measure to the nearest degree of the angle between two forces. So now we're looking for the angle that connects the two forces, okay? Of 20 pounds and 15 pounds if the magnitude of their resultant is 28 pounds. They have it set up for you already. Remember, this is also 15, okay? We are looking for the angle in between. If we can solve for this angle, then, see, they're looking for the cosine of ABC. If we can solve for this angle, then we can go reverse and solve for this one, because this is the one that we actually want to know, okay? We want to know the angle between the two forces. The two forces here are acting on point A. The resultant is coming out of there, pulling the same amount of force, right? So we want to know this angle, but we only have enough information right now to solve for this one. And that's what they're doing here with the law of cosine. And they discovered that this angle is 105.37 degrees. Remember, don't round too early, okay? Subtracting that from 180, they discover that this is 74.6 degrees. And then they round at that point to approximately 75 degrees, okay? All right, let's take a look at some of these problems together. We're going to start here. Wow, my book is really scuffed up today. We're going to start here on page 31 with number 9, okay? For problem number 9, it says the magnitude of the resultant vector shown is how much, okay? What is this magnitude of this resultant vector? So remember, the magnitude is how many pounds, how long it is, okay? So they have given us this degree of 30. This is the square root of 3, and we have a theta over there. What they don't make very clear, but it is vital to solve this problem, is that this is a right angle right here, okay? If they didn't make it clear, so make sure you mark it down. That is a right angle. It's the only way to solve this problem, because they gave us 2 pieces of information. It's just not enough. But now it is, right? So we know that this is a right angle. So we can say that the sine of 30 degrees is equal to the opposite over the hypotenuse, right? So the square root of 3 over the r. Multiply both sides by r. And now we have r sine of 30 degrees is equal to the square root of 3 divided by the sine of 30 degrees. Okay. R is equal to, and their answers are indirect, or not direct, but exact answers. So r is going to be equal to the square root of 3. And remember, the sine of 30 degrees, if we are using our little chart here, which is in unit 3, page 75, the sine of 30 degrees is 1/2, right? We can't have a fraction in the denominator, so we're going to multiply by the reciprocal. So r is equal to 2 times the square root of 3, which is letter A. All right? Okay. Keep those, keep those charts we've talked about in the past. Keep them on hand, because they're always going to be useful. 2 forces act at right angles at a point on a body. Okay, I'm just going to go ahead and draw them, okay, because that's how I do. One of the forces is 120 pounds, and the other force is 160 pounds. Find the magnitude of the resultant of the 2 forces. Okay, right angle, right angles, right angles. This is coming up this way, okay? Find the magnitude of the resultant of the 2 forces. So this is 120, this is 120, this is a right angle. Pulling it out so you can see it, we've got 160, and I know the drawing is obviously not to scale, we're going to ignore that part for now. We need to find this Pythagorean theorem, okay? So 120 squared plus 160 squared is going to equal C squared, all right? We'll call that our C. All right, grabbing my calculator. Okay, 120 squared equals 14400. 160 squared equals 25600 equals C squared plus 14400. So it equals 40,000. And we take the square root of 40,000 and we get 200. Okay, so the magnitude is 200 pounds because that's the unit of measure we have, which is letter B. All right. I always am going to draw it out 99.9% of the time. I like to see what's happening. Okay, let's turn the page and do some more. All right, we're on page 32. Let's take a look at number 14. Two forces of 7 newtons and 11 newtons act on a body at an angle of 60 degrees. Okay, this is 60 degrees. Here's my 11, here's my 7. Okay, find the magnitude of the resultant force to the nearest whole number. Okay. Again, we are looking for this force, okay? This is an 11. If this whole angle here is 60, what is this angle here, right? Remember, they're supplementary. Adjacent angles are supplementary in a parallelogram. So if this whole angle is 60 degrees, then this angle here is 120 degrees. So we have two sides and an included angle, so we're going to be using our cosine, law of cosines, right? So x squared is going to be equal to 7 squared plus 11 squared minus 2 times 7 times 11 times the cosine of 120 degrees, right? That's what we're looking for here. So x squared is equal to 49 plus 121, all right? And then let's do this other part here. Turn this back on. We have 2 times 7 times 11 times the cosine of 120, close my parentheses, equals. Now, there's a negative in the formula. The answer just happens to be also a negative 77, okay? So I have 49 plus 121 minus 77. We can't have a minus, so it becomes a plus. So plus 77. X squared is equal to 247. We take the square root of that answer, closing our parentheses, equals x is equal to 15.716. I'd like to go usually to 3 decimals just in case. It says to the nearest whole number, so I'm rounding a 5 based on a 7, so it's going to be equal to 16 newtons. Okay, let's do one more together. Number 15. The resultant of a 15-pound force and an 8-pound force acting on an object is 10 pounds. The angle formed to the nearest degree between the resultant and the smaller force is how much? Okay, I'm drawing it out. I've got a force and a force, right? And those forces keep on going. We'll call this one the 8, and we'll call this one the 15. This is 10. They want to know the angle formed to the nearest degree between the resultant and the smaller force. They want to know this angle here, right? So that is not a problem to figure out. Remember, this is going to be 15 and this is going to be 8. That's how parallelograms work. So we're going to use the law of cosine again, except this time we don't have the angle measurement, but we have its side. So it's going to be 15 squared, because that's what's opposite here, right, is going to be equal to our adjacent sides of 8 squared plus 10 squared minus 2 times 8 times 10 times the cosine of x, theta, whatever you want to call it. We'll call it theta. 15 is 225 equals 64 plus 100 minus 160 times the cosine of theta. Okay. So 225 is equal to 164 minus 160 cosine theta. We are going to subtract 164 from both sides. So 225 minus 164 is 61 is equal to negative 160 cosine theta. We're dividing by a negative 160 on both sides. So divided by negative 160. So I end up with a negative 0.38125 equals cosine of theta. I'm going to hit shift inverse cosine, answer, close the parentheses, equals. So theta is equal to 112.411 degrees. Okay? 112.411 degrees. Now, the instructions read to the nearest degree, so we're rounding a 2 based on a 4, so it's just going to be 112 degrees. Okay? So that's this first part of section 2. Go ahead and finish the rest of these and then meet me back here for the next part. The next part of this section begins here on page 33. It's called vector components. I don't normally read from the top sometimes, but very, very seldom. This is actually kind of funny, so enjoy it if you'd like. But we're going to jump right down here to a position vector. It says many computer graphic systems use vector equations to represent images, and vectors are used to describe the motion of an object in space with relation to a fixed point, right? We're talking about a fixed point. In the rectangular coordinate system, position vector is a vector whose tail or initial point is at the origin, right? X and Y are the components of the position vector. These components can give us a magnitude of the vector, okay? So the magnitude of vector R is the square root of x, the quantity x squared plus y squared, okay? And the direction of the angle would be the tangent, or y over x, all right? And then it says here, did you know in three-dimensional space, the coordinates of the position vector are given as x, y, z? Okay, something to think about. Here's our first example. A position vector has a terminal point at -4, 2. What angle does the vector make with the positive x-axis? Okay. Here's our solution. I like to graph it, so we're going to do that real quick. Okay, it's at -4, 2. So it's like right here. It went like this. Here's my -4. +2, which tells me that this is -4 and this is a +2, right? Recall that taking the inverse tangent of a negative value on the calculator will give us a fourth quadrant angle, okay, which is -26.57 degrees. The vector, however, terminates in quadrant 2. So we must use the angle to determine our reference angle, which is, we subtract it from 180 degrees, okay? So remember, when you solve with the tangent, which is 2 over -4, right? You get -26.57 degrees. That is this reference angle. Remember that from a few books back, right? That's the reference angle. So we have to take 180 degrees and subtract that to get this this is the angle that we want, right? And that is 153.43 degrees. All right? Okay. Let's turn the page. Here at the top of page 34, we read that the sum of two position vectors can be found by adding the components of the vectors. Add the x components and add the y components to get the terminal point of the sum. Here's an example. If u and v are vector u, vector v, are position vectors with terminal points at -2, 5 and 3, 1 respectively, which means u is the negative 2, 5, v is 3 and 1. Find the terminal point u plus v and the angle it makes with the horizon, okay? X sub u plus x sub v, comma, y sub u plus y sub v gets me at 1/6. The tangent, now remember, when we were talking about the unit circle, right, and we're talking about coordinate pairs, the cosine is technically the x value and the y is the sine value. So for the tangent being sine over cosine, it's 6/1. So it's an 80-degree angle. So the position is 1, 6 with an 80.5 degree angle. All right, not too bad. All right, let's look at force. And perhaps you've looked at force before if you've taken a physics class, because it says here in physics, one must use the components of forces acting on an object to solve problems, okay? Use the trigonometric functions results in this array. They're reminding you what those look like, but let's just jump in here and take a look at these problems, okay? So at this example, top of page 34, second column, find the horizontal and vertical components given that the resultant force R is 42 pounds and theta is 80 degrees. They want you to solve for u and v, our x value technically, and our y value. They've given you the angle and the resultant. Now, before we actually solve this one, I want to come back to here real quick. OA, okay, is our u value. So OA, I'm going to just call it u, is equal to OB, which is the resultant, right, times the cosine of theta. AB, which is our v, is equal to the resultant again, times the sine of theta, okay? So that's what they're doing here to solve these. That's what this means. We just have rewritten it. Feel free to take that note down. It's going to be important to do some of these problems, right? So to find u, which is this horizontal movement, right, we are going to take the resultant times the cosine of theta. And we get 7.2932. To find v, we're going to take the resultant times the sine of theta, which is 41.3619. That way. Okay? That's all they're doing here. So these are interesting, and they are very specific to this drawing, but this is what's happening here. Okay? So in this next one, it says, resolve a force of 10 pounds into equal components and determine the measure of theta and, I forget what that is. Theta? No. Phi or something like that. I forget. One and the other, okay? If they are equal, that tells me that the forces are equal, right? F sub 1 is equal to F sub 2, which either way you want to go. That tells me that this is a square, and the diagonal of a square cuts the angles in half, which means this is a 45-degree angle and this is a 45-degree angle, right? That much we know for sure. So they want to know, determine the measure of the alpha and theta. They're both, or whatever, theta, these two angles, they're both 45 degrees, okay? But they also want to know, what is the force? Well, if we remember our 45, 45, 90, we would know that the hypotenuse is equal to the leg times the square root of 2. So if they solved it a little bit different down here, but I'd like to stick to the things that we know. And so they did that 2f squareds are going to equal 100 squared, right? F squared plus, or f sub 1 squared plus f sub 2 squared, which would be both f's, they're the same. So it's f sub 1 squared plus f sub 1 squared gives me the 2f sub 1 squared. So they're doing the Pythagorean theorem, equals 100, then they solved it, right? But we could just do this. So we could just say that 10 is equal to the leg times the square root of 2. Divide both sides by the square root of 2. The leg is equal to 10 divided by the square root of 2, but you know we cannot have a square root in the denominator, so we multiply the square root of 2 by the square root of 2, and we get 10 times the square root of 2 over 2, which reduces to 5 times the square root of 2. Okay, you could do it either way. You could do the Pythagorean theorem. You could use the 45, 45, 90 rules that we've learned in the past and know that the hypotenuse is equal to the leg times the square root of 2, because the legs are the same length. They don't look it in this drawing, but they are. Okay, so 45 degrees is the direction. The magnitude is 5 times the square root of 2 pounds, because that's what they've given us. All right. Okay, next example, page 35. Two forces, one of 10 pounds and one of 8, act at a point on a body at right angles. Okay. Find the measure of the angles to the nearest tenth of a degree between each component and the resultant. So they want to know what is this and what is this. That's what they want you to solve for. Together they make 90, but we want to know each one individually. If this is 8, then this is 8. If this is 10, then this is 10, right? So if I'm solving for, which one did they do first? They're doing this one first. If I'm solving for this one first, the tangent is equal to 10 over 8. They solve and find that this one is 51.3 degrees. Now, they do the tangent to solve for the other one, but all you had to do was subtract this number from 90 to get this other side, right? Because it says right angles. So we know that this is a 90-degree angle. But either way, it's fine. They did it again. Except they did it in this one. The tangent was 8 over 10, and they solved 38.7 degrees, all right? Okay, that's those. Now we're kind of starting a new topic. It's still force, right? But it's on a different level. So we've got some things to talk about. An object resting on a horizontal surface has two forces acting on it. The force of weight, pulling it down, and an opposite force pushing up on it called the normal force. Okay, it's what keeps it from moving from side to side or whatnot. When an object is on an inclined plane, a ramp, okay, the force of the weight is broken down into horizontal and vertical components, right? The normal continued straight through is considered the vertical component. Horizontal component, let me read the whole thing. The horizontal component of the weight is parallel to the surface of the inclined plane. Okay, it's parallel to the inclined plane. The vertical component is opposite the normal force, like I said a minute ago, perpendicular to the surface of the inclined plane. This is perpendicular right here. Okay, perpendicular to the surface of the inclined plane. Right? The weight pulls down this way and is actually perpendicular with this line here. Okay? The angle formed by the weight of the object and its vertical component is equal to the angle of inclination. So this angle here is equal to this angle here. That's what they've done by putting the red theta in each one. Using right triangle, the cosine of theta is going to be V over W. This over this, okay? If we solve this for V, then the vertical component is equal to the weight times the cosine of theta. And that's what it says here. The vertical component is equal to the weight times the cosine of the angle of inclination. The force opposite the horizontal component is called friction force. Now, it's going to be on the next page, but you know, they're talking about it here. So friction force goes this way. It's opposite the horizontal component. This force keeps the object from sliding down the plane. Friction keeps it from sliding down. Let's turn the page. here it is. The friction force keeps it from sliding down the plane, right? In the following diagram, weight times the vertical component is equal to the horizontal component of the weight. Okay, so the horizontal, which is equal to the friction because they're opposite but equal, okay, is also equal to the weight times the vertical, which they didn't draw here. It's down here though, okay? It's a lot of things. Using the right triangle, we can solve for the horizontal component, resulting in the horizontal or the force, because they're opposite each other. The only difference is the direction. The horizontal is going to equal the weight times the sine of theta. So this is an important formula. Anytime they have their formula and then they actually write out what it says, those are important ones. So horizontal component is equal to the weight times the sine of the angle of inclination. All right. Looking at an example, they only give us one, so don't feel like this is going to be crazy complicated, okay? A block of wood weighing 6 pounds, so our weight is right here, 6 pounds. I wish they would draw it like this since it's our first problem, but that's okay. They decided to give us more three-dimensional, which, you know, is fabulous. All right, anyway, 6 pounds. Right here, my 6 pounds. Rests on an inclination plane that makes an angle of 20 degrees with the horizontal. Okay, 20 degrees. That means this is 20 degrees. This is 20 degrees. We have a 6 and a 20. How much of the friction force is needed to prevent the block from sliding down the plane? Now they've changed some of the letters, but we're looking for this, okay? And we just had the formula for this, which is H equals the weight times the sine of theta. H, of course, is the other way, but the force, and did I forget to read something about that? Oh, it's up here. Sorry, I knew they said something. Remember, Newton's third law is for every action or force, an equal and opposite reaction occurs. That's what this friction is, equal but opposite, okay? So if we solve for H, we're solving for the friction as well. So to do that, we just need to take the weight times the sine, right here, the weight times the sine of the angle of inclination, all right? And we find that it is approximately 2 pounds. So the force needed to prevent the block from sliding down the plane is 2 pounds. Now, it doesn't ask us what direction or any of that stuff. They just want to know the force. And so this formula is what we used. Okay? Let's do some of these problems together. Number 18. All right. Given f sub 1 is equal to f sub 2. Okay, again, 45, 45, 90 triangle then, right? Well, we know it's a right triangle because it tells us right there that they are perpendicular to each other. What is f sub 1? Remember, in a 45, 90 triangle, the hypotenuse is equal to the leg times the square root of 2. Make a note of that if you don't remember learning that in algebra, geometry, algebra 2, okay? You should have learned that in the past, and it's all right if you don't remember because, you know, sometimes we don't remember everything. But that is an important formula for using here with this type of work. So the hypotenuse is equal to the leg times the square root of 2. So 5 times the square root of 2 is equal to L times the square root of 2. If we divide both sides by the square root of 2, then the leg is equal to 5, which is letter C. All right. Now, you could have done the Pythagorean theorem just like the book example did. By all means, if that's how you want to solve it, go right ahead. As long as you're getting the right answer, that is. Okay. Number 19. Approximately what angle does the position vector whose terminal point is 11, 3 make with the positive x-axis? So I'm going to super simple sketch. 11, 3 is going to be way up here, right? Something like this. They want to know this angle. This is 11. Oh, I guess I kind of drew that backwards, didn't I? All right, well, that's fine. 11 comma 3. I guess it would be more way over here, right? But that's okay. 11 comma 3. What are they asking us? Oh, what is this angle? Well, the tangent of this angle is 3 over 11, right? So the tangent of theta is going to be equal to 3 over 11. So grabbing our... Oh, I am so sorry for that amount of noise. This is... My workspace is cluttered, for sure. Sorry. All right, anyway. 3 divided by 11, okay, is 0.27272727. We want the shift tangent to the -1 of the answer. Close my parentheses. Equals. I'm down here. Not the tangent. Theta, because we already solved that. Theta is going to be equal to 15.255 degrees. It doesn't say whether they want us to round, but they do because the closest answer right here is 15, right? 5 rounding on a 2, it's going to stay the same. So the answer is B. Okay, let's turn the page and look at a couple more. Taking a look here at page 38, number 25. If 100-pound block of ice is placed on an inclined plane so that it makes an angle of 35 degrees with the horizontal. Okay, I'm drawing it. Here's my horizontal. Here's my incline. This is 35 degrees. Here is my block of ice. No, I'm not an artist. But the block weighs, so remember my weight comes down here at a right angle, and it is 100. I don't really have enough space here. I should have drawn that over there. Okay, this is 100 pounds. I still didn't barely fit in there. And my angle here, we'll do it this way, is 35 degrees, right? Because this is 35. So that's 35. All right. How much friction force will be required to keep it from sliding down the plane? So we're looking for the friction force, but remember, H is equal to the weight times the cosine of theta. Yes. Oh, no, it's the sine. Check your formulas. The sine of theta. Okay. It says, choose the equation that could be used to solve the problem if X represents the force required to keep the block from sliding down the plane. So instead of H, we are doing X. So X is going to equal 100 times the sine of 35 degrees. Okay, so X equals 100 times cosine, no. X equals 100 times the sine of 35, which is letter C. We did it. All right, they don't want us to actually solve it, so we won't. All right, let's not do more than we need to. 26. A block of wood weighing 18 pounds rests on an inclination plane that makes an angle of 60 degrees with the horizontal. Ooh, that's a steep one. Okay, here's my block of wood. And 18 pounds. Okay. Here is my, right, because it goes straight through my block of wood. Okay. To the nearest pound, how much friction force is needed to prevent the block from sliding down the plane? All right, so H again is equal to the weight of 18 times the sine, oh, I forgot to write it, of 60 degrees. Okay. Calculator. All right. Sine of 60, close our parentheses, equals, so H is equal to 15.588. How much friction force is needed? To the nearest pound. So we're rounding a 5 based on a 5, so it's going to be 16 pounds. Okay. All right, let's do this one more together because it's got a lot going on here. So let's just work on this together a little bit, okay? An iron ball weighing 10 pounds, okay, so here's my weight of 10 pounds, rests on 2 smooth plane surface boards that are inclined at 30 and 60 degrees to the horizon. So here's a 31 and here's a 61. To the nearest whole number, what is the pressure on the board from the force of F sub 1. So I want to solve what is the amount of pressure from this force of F sub 1. That's what I'm looking to solve. So if this ramp or inclination, sorry, is 30 degrees, then this right here is also 30 degrees, just like it was here, just like they're the same on this one, right? Here's the weight coming down, here's its force, so that is the 30-degree angle. So the cosine, because we have, let's see here, a right angle is the force over 10. So the cosine of 30 degrees is going to equal adjacent, which is the force sub 1, over hypotenuse, which is 10. All right, multiplying both sides by 10. We get 10 times the cosine of 30 degrees is equal to the force sub 1, which is what we're trying to solve for, okay? So 10 times the cosine of 30 degrees, close my parentheses, equals, the force sub 1 is equal to 8.660. To the nearest whole number, we're rounding an 8 based on a 6, so it's going to be 9 pounds, which is letter C. All right, so remember how this gets set up. Normally I would be like, oh, look at the back of the book, and they have, but this drawing right here is pretty important. Keep referencing this, page 36. The back of the book doesn't have the drawings. I like the drawings. Now the back of the book has everything written out. If that works for you, then make sure you reference that. But if the drawings work better for you, then make sure you are referencing that drawing. Okay? All right. Go ahead and finish the rest of these problems and meet me back here for this next section about applications. All right, there are two parts left of this section, and this one that we're working on now is called navigation application. It's on page 39. Again, a lot of vocabulary here. So make sure you are making yourself at least somewhat familiar with that before we jump into the part here. I'm going to read some of this at the bottom. It says navigation problems involve vectors because moving objects have a magnitude, a rate of travel, such as 5 miles per hour, and a direction. The flight of an airplane is affected not only by its own speed and direction, but also by that of any wind that may be blowing it off course. Okay. Similarly, boats have the force of the water's current impacting their navigation. So we need to figure out how we can properly decide where they're headed, right? Which way they're going. So we're going to turn the page. All right, they're jumping right into an example. So we know we can take this, right? A man who can row in still water at 5 miles per hour heads directly across a river flowing at 6 miles per hour to the nearest tenth of a degree. At what angle to the line on which he is heading does he drift downstream? Here's our angle. So he is rowing at 5 miles per hour. The river is flowing at 6 miles per hour. What is the measure of this angle? Okay, this is always going to be a 90 degree. So the tangent, because we don't have the hypotenuse, of theta is 6/5. So the angle that he is being pushed off course, basically, is at 50.2 degrees. All right, not too bad. Now, here is some information. Problems involving airplane navigation require you to be familiar with the vocabulary associated with it. Knots, nautical miles, heading, track, course, airspeed, ground speed. Go ahead and read through those. Oh, wait, there's more here. Tailwind, headwind, drift angle. Now, this next part is kind of important to our drawings that we're going to be working with. So I'm going to make sure I read through that. Pause it and read those other definitions if you haven't already. But going on. In modern navigation practice, courses and bearings are generally measured clockwise from north and range anywhere from 0 degrees up to 360. The following heading or bearings are illustrated. Okay. 135 degrees you start at north and go clockwise, 330 all the way around. 42, north 28 west. So now you're going, starting at the north, but you're going 28 west from there, okay? North 42 east was this one, so we went towards the east. North 42 west says we went 28 degrees to the west. South 73 degrees west means we're starting at the south and going 73 degrees west towards the west. Okay, so those are important to do as we draw our work as we move forward. So page 41, this example here. A radar operator in an airport control tower, so the tower is T, observes two airplanes flying toward each other along a straight line. So they're basically flying directly towards each other. One plane, A, flying at 520 miles per hour, has a bearing from the tower of 40 degrees. So here's plane A. Its bearing from the tower, 40 degrees. If it just says 40 degrees, you start at north and you go clockwise. And is 20 miles from the tower. 20 miles from the tower, 20, okay? The other plane B, flying at 460 miles per hour, has a bearing from the tower of 50 degrees. So north 50 is plane B, and it is 25 miles from the airport. They are heading toward each other, remember? How long, to the nearest second, do the pilots have to take evasive action provided they are alerted at once by the control tower? How quickly do they have, how much time do they have to move before they crash, is what this is asking, or, stating. So the problem asks how long it will take to close the distance, little c there, between the two planes, and it's represented by the little c. We have two sides and an included angle, right? This one was 40, this one is 50, so this one here is 10 degrees. They use the law of cosines to solve that C is 6.34 miles. That's how many miles apart they are. Now, that's not what they're asking, though. They're asking how much time do they have? Well, the airplanes are flying at each other, so we have to add their speeds. Together, their speeds coming together is 980 miles per hour, okay? If we take the distance divided by the speed, we get 0.00647 hours. There's 3,600 seconds in an hour. We multiply and get 23.3 seconds. Not much time. They better act fast. Let's turn the page. At the top of page 42, we have another example. A pilot is headed in a direction of 74 degrees. Okay, so from north, 74, here's a pilot. Wind blowing 40 knots from the direction of 132 degrees. So from north, 132 degrees. The wind always blows opposite. Like the inclination would be to draw the arrow going this way, right, at 132, but it always blows opposite. So we're going to straighten that line all the way through so that our wind is blowing that direction, okay? If she is to fly an airspeed of 220 knots, what will her ground speed be? In what direction will she be headed? So in our drawing, right, this is the speed of the airplane. This is the speed of the wind. We finish off our parallelogram, okay? And we draw our resultant, which is our ground speed. All right? So, that being said, we just solve this like we've normally been solving a lot of these problems. Now, the example here has a lot of angle measures, which is necessary, right? She is flying at 74. Remember, the air is blowing at 132 degrees. What they figured here for AON being north, this little bit, right? They've taken 180 degrees and subtracted this 132. it actually gives you this measure, but these are vertical angles, so they are equal. And that is 48 degrees. So this measure here is 48 degrees. If you add the 48 and the 74, you get AOB, which is this whole side of our parallelogram. So I'm going to kind of take this parallelogram out. Okay, and so this angle here is, what did I say, 122 degrees, right? If this angle is 122 degrees, then we can subtract that from 180 and get OBC, which is this angle, which is 58, because adjacent angles in a parallelogram are supplementary. So now we know both of these angles. We're solving for this. So what we really needed was that 58, right? And remember, this is the 220 miles per hour the plane is flying, and this is the 40 knots the wind is blowing, okay? So now with that information, we can solve for the resultant, which is what they do here with the law of cosines, and find that the resultant is 202 knots, okay? Now they also asked, well, what is the direction? Okay, to figure out the direction, we need to solve for COB, which is this little piece of it right here, okay? To solve for the COB, they used the law of sines, and figured out it was a course direction of 64 degrees. So those are your two answers for that problem that they're asking, okay? This next example says, find the course, ground speed, and drift angle of an airplane headed at 140 degrees and flying at an airspeed of 240 miles per hour when a 30 mile per hour wind blows from a direction of 40 degrees. Okay, so remember, you measure the 40 degrees, and instinctually you want to draw the arrow this way, but you're going to draw it this way instead. It goes opposite of the degree measure that it is for drawing purposes, okay? So we've got it set up. They set up the parallelogram, okay? They want to know the course, the direction, the degree measure, right? The ground speed, which is our OC in this case. And the drift angle, okay? The drift angle meaning the airplane wants to fly this way, but they are being forced this direction. So this is the drift angle right here. All right? To figure out this angle here, we can say that that's 40 degrees, right? This is a vertical angle, so we know this angle measurement is 40 degrees. If we add that to 180 and then subtract this 140, okay, we get that AOB, this whole thing, is 80 degrees. So the 40 degrees plus this 180 gets us all the way to here, okay? That's what that first part is. This big angle here. Then by taking away this piece, we're only left with this, okay? So again, if we redraw just our parallelogram, which looks quite a bit more like a rectangle, but that's okay. All right, here's our 30, here's our 240. We've got this angle here being 80 degrees, right? We're trying to solve for this, so we need to solve for the other angle. Well, if this is 80, then this one is 100 degrees. And remember, if that's 240, then this is 240. Just like if that's 30, this is 30, okay? Now we have this set of measurements to solve for the resultant here, all right? So they're going to use the law of cosines and solve to find OC, which is 247.0 miles per hour, right? That's the resultant. That's what we found, okay? Now they want to know, that's the ground speed, okay? They want to know the course and the drift angle. Okay, so we need to figure out what this is, and we can find the drift angle, and then we can find the course as well. Okay, using the law of sines, because remember we're trying to find this piece right here, right? We use the law of sines to solve for COA, that little piece right here, at 6.8 degrees. Okay, so they're saying the drift angle is 7 degrees. That's okay, they rounded, that's their prerogative, right? The ground speed, remember, was 247 miles per hour. The course angle is 140 degrees plus that 6.8 or 7 since they rounded, so 147 degrees is the actual course angle. All right, so starting off with a drawing like this, fine and dandy. It gets a little cluttered. If you want to redraw your parallelogram so that you have an easier workspace, then by all means. Okay, all right, let's do some of these together. Looking here at problem number 38, it says a balloon is rising vertically at a rate of 12 feet per second. At the same time, it's being blown horizontally by a wind of 18 feet per second. Find the angle its path makes with the horizontal by the wind of, because it's being pushed by the wind, right? So remember, this comes here like that. Okay, we're looking for this angle. This is a 90-degree angle, okay? If this is 12, this is 12. If that's 18, this is 18, okay? We are solving not for the resultant, because that's not what they're asking for. They want this down here. And we have an opposite and an adjacent. So the tangent of theta is equal to 12 over 18, okay? Grabbing our calculators. We have 12 divided by 18 equals, so the tangent of theta is equal to 0.6666 repeating, okay? We are going to do our second tangent of the answer, closing our parentheses, equals. So theta is equal to 33.69000, okay? They obviously want us to round to 34, so the answer is A. All right, simple trigonometry for that one. All right, let's turn the page. Top of page 44, looking at problem 39, it's a very similar problem, okay? A balloon is rising at a rate of 10 feet per second, but it's being pushed by a wind at 5 feet per second. It says find the angle it makes with the horizontal, okay? So again, we're looking for this angle. And if that's 5, this is 5. If that's 10, this is 10, okay? So the tangent of x is equal to 10 over 5. Or the tangent of x is equal to 2, right? So what is that? We're going to do shift or second tangent 2, close our parentheses, equals x is equal to 63.4349. I'm assuming they want us to round, and it would be C, 63. All right. Okay, let's take a look at number 42. For 42, it says an airplane with a speed of 160 knots, okay, our airplane is here, is headed east while a 24-knot wind is blowing from 240 degrees. Okay, explain how you would use the results of finding the ground speed. Explain. It's not an actual problem. I'm not an explainer. Let's do 41 instead. Sorry, I hadn't read that one ahead of time. Oops. An airplane with a ground speed of 160 knots is headed east while a 24-knot wind is blowing from 240 degrees. Find the ground speed to the nearest tenth of a knot. So they've drawn the ground speed in, right? This is our parallelogram. It's going to look like this, okay? So this is the one we need to figure out. So this angle here or this angle here is what we need to know, okay? If this is 240 degrees, thinking of our unit circle, right? This line here would be the 270 mark. So if I take, well, 270 minus 240 is 30. So this down here is 30 degrees. This little angle here, okay? 30 degrees, this is, the rest of this is 180, right? This line here is supplementary. So all these angles that are in here make up 180. So if I have 30 here, then this angle, and let me redraw this. It's kind of a sharp parallelogram here. This angle here is 150 degrees because that's what we need to make up our opposite ends and forming a straight line, right? So this is 150. That is what we need to know to figure out our ground speed, which is this arrow here. This is 160, and this is 24, and this is what we're trying to solve for. Okay, so we're going to use the law of cosines, which tells me that x squared is equal to 160 squared plus 24 squared minus 2 times 160 times 24 times the cosine of 150 degrees. So it went off the page. Okay. Clear that out. So 160 squared is equal to 25600. 24 squared is equal to 576 minus 2 times 160 times 24 times the cosine of 150 degrees, close my parentheses. Okay, so the minus here is part of the equation. This cosine is negative, so 6651.075. We can't have a minus in math, so that becomes a plus, okay? So I'm going to times this by a -1 just to make it a positive. And then I'm going to add 576, and I'm going to add 25600. And I get x squared equal to 32827.075, taking the square root of that answer, close my parentheses, and x is equal to 181.182, but I think 0.18 is enough because they want you to round it anyway, so 181.2 knots. All right, let's do one more since we didn't do 42 together. Two airplanes take off from an airport at the same time. One travels on a heading of 45 degrees at 420 miles per hour, and the other at a heading of 150 at 400 miles per hour. After 2 hours, how far apart are the airplanes? Okay, let's draw our north, east, south, west. One plane is at 45, right? So this is 45. Okay, and the other is at 150. Okay, so the other one is down here, like maybe this far, and that is 150 degrees. We'll deal with the miles per hour thing in a minute. Okay, I just want to get my parallelogram set up. Okay. And so then I'm going to redraw it over here. My 150 maybe is like this, and this one. So I kind of took it here and sat it down, okay? Now, this is 150 degrees. If we take away 45 of those, then we have 105 degrees, right? Right? Am I thinking about this right? Minus 45? Yeah, 105 degrees. Okay. All right. Psyching myself out a little bit there. We want to know the distance in between them, so we are trying to solve for this. Okay. Now, here's the part you need to think about. This plane up here is traveling at 420 miles per hour, but it did it for how long? For 2 hours. So it's gone 840 miles. Okay. This plane down here, this piece, because remember I just clunked it over, this piece down here is traveling 400 miles per hour for 2 hours, so he went 800 miles. Right? That's the numbers we need to make sure we're using in our law of cosine. So x squared is going to equal 840 squared plus 800 squared minus 2 times 840 times 800 times the cosine of 105 degrees. Right? So 840 squared is a honking number, 705,600 plus 800 squared, which is what, 640,000? Yeah, 640,000 minus 2 times 840 times 800 times the cosine of 105 degrees. Remember, negative is part of the equation. This negative 34785.2.79. We'll stop there. This negative is here. We can't have a negative in math, so it becomes a positive. I want to make this a positive, so I'm going to times it by -1. Then I'm going to add the other numbers. So I'm going to add 640,000 plus 705600. So my x squared is equal to 1693452.79. Taking the square root of that answer, close my parentheses, and I see that x is equal to 1301.327, 1,301 miles. They're having us round a 1 based on a 3, so it's letter C. Okay, so once you get the bearings, I find it very useful to redraw the parallelogram away from all of this, because it just is a lot, right? As long as you can figure out what your angles are, make sure you're putting them in the right places, you shouldn't have a problem, okay? If you are a visual person like me, anyway. All right, go ahead and finish the rest of the problems we didn't do together, and join me back here for this last part of section 2. The final part of section 3 begins on page 45, and it's titled Vector Multiplication. It says, in the head-to-tail method for adding vectors, adding a vector to itself results in a vector with the same direction, but with double the magnitude. When a vector is multiplied by a scalar, the result is just an increase in its magnitude, right? So here's this vector, 2v is double, right? 1/2 is smaller, right? Half the size, okay? It's a change in the magnitude. The negative of a vector is a vector with the same magnitude, but in the opposite direction. We can think of the negative vector as -1 times a vector. Multiplying the coordinates of the terminal point of a position vector, by -1 will give us its negative. All right, let's turn the page. Here at the top, it says at top of page 46, you can subtract vectors by expressing the difference as a sum. So if you're taking u minus v, it's the same as u plus -v. Now, if you have an issue with distributing your negative sign, this might be a way to think about it, okay? Algebraically, position vectors can be subtracted by subtracting the coordinates. So let's take a look at this example here. If m and n are position vectors with terminal points at 2, 3 and 4, 1 respectively, so 2, 3 is m, 4, 1 is n, find m minus n. So basically, oh, they do it down here. They've plotted all the different points, right? They plotted m, they plotted n, okay? They plotted -n, so they changed it to a negative point, and then they added them, okay? So 2 plus -4, 3 plus -1. Now, you could simply have taken 2 minus 4, comma, 3 minus 1, and gotten the exact same answer, okay? It would be -2, comma, 2. Okay? Either way is fine. I don't know. I don't think we'll be asked to plot them on the homework, but perhaps. Okay? But that's it. We're just subtracting the x from the x, y from y, right? Over here we have vectors times vectors, okay? There are different types of vector multiplication. The product may be a scalar or a vector. The dot product will be addressed here. There's a couple of types of vector multiplication, but we're only going to be working with the dot product. The dot product of two vectors results in a scalar. The scalar product is what it's called. It says, recall from geometry that the projection of a point on a line is perpendicular from the point to the line. So if you should have learned this in geometry, but the geometry I teach, it just kind of glances over it. It doesn't spend a lot of time. The projection of A is basically if the sun were here shining down, right? It would be A's shadow. So A's shadow is going to fall down perpendicular on B, right? The shadow of A, or the projection of A, can never be longer than A. It can be the same length as A, but it can never be longer than A because the sun is always here. It's not like a afternoon shadow or anything. Okay, the sun is always directly above. If you think about it as a shadow way, right? That's what the projection of A is, okay? Comes right down. The projection of A on B is the x component of A, which is given by the magnitude of A times the cosine of theta. The dot product of A and B is defined as this x component of A times the magnitude of B. So now we have the magnitude of A times the magnitude of B times the cosine of theta. The projection of a vector on itself is the magnitude. The angle between the vector and itself is 0 because the vector is overlapping. We're talking about just squaring it, okay? We'll look at some examples in a minute, all right? Engineers use a dot product to calculate work. Work, which is scalar, is the dot product of two vectors, force and displacement. So work equals force times displacement, distance. In cases where the force is not in the same direction as the distance, the horizontal component of the force is used in calculating the work. Okay, so up here on page 47, it breaks down to, here's our box, here's our force, here's our distance, right? Work is going to be the magnitude of the force times the magnitude of the distance times the cosine of theta. Right? Another formula is here. This is probably the one we're going to be using more often. Vector A times vector B is A sub x times the B sub x plus the A sub y times the B sub y. Okay? Let's take a look at, they're reminding us of this cosine of two angles subtracted from each other, right? And that's that formula. That's just a reminder. Let's take a look at example here on page 47. U and V are position vectors whose terminal points are at 3, 4 and 5, 12 respectively. Okay, so U 3, 4, V 5, 12. Find U times V. In this first solution, they find the magnitude of U and the magnitude of V. They find the angle measure between them. Then they put it into that formula here, this one or this one, okay? They're pretty much the same. And they find that U times V is 63. That's a lot of work. Solution 2, if we just do this part, we would take 3 up here, right? 3 times 5 plus 4 times 12 and get 63. So while these formulas are fabulous and have a definite purpose for this type of problem, this formula here is the one we want to use. Okay, there's no reason to go through all of this and possibly make an error in that process when we can just do that. All right. The let's review tells me that our homework problems are on the next page, so let's turn the page and do some of those together. We are on page 48. Let's take a look at problem number 51. If a position vector v has a magnitude of 5 and is located in the first quadrant, which of the following could be the terminal point? All right, so I'm just going to draw my first quadrant. My magnitude is 5, okay? I like to see what I'm working with. So they're saying which of these points could be the terminal point to v? Well, first of all, we have to think about what is just v. So I'm going to start with a, right? And I'm going to divide it by 2. So 1/8 would be 2v. So 1v would be at 1, 4. Now, if I put a 1 here and a 4 here, it doesn't really matter which where the 4 could go here, the 1 could go here. Are they going to Pythagorean theorem into having a hypotenuse of 5? Well, no, right? Because 1 squared is 1, 4 squared is 16. The square root of 17 is not 5. So A does not work. B, then, half of that would be at 2, 3. If I put 2 and 3 here, 2 squared plus 3 squared is 4 plus 9, which is 13. The square root of 13 is not 5. So it is not B. C, half of 6 and 8, 6, 8 is 3, 4. And we dealt with these triangles quite a bit, right? A 3, 4, 5 triangle. So 3 squared plus 4 squared is 9 plus 16, which is 25, which would give us a magnitude of 5. So the answer is C. I don't really know any other way to figure that out. Let's just look at D, because maybe when you first glanced at this, you thought, oh, it's got to be D, right? Well, for D to be true, then our regular V point would be at 5, 5. And 5 squared plus 5 squared, right, is 50. The square root of 50 is not going to be 5. So it's not D, even though maybe that's the one that jumped out at you at first. All right, that is the only way that I could think to solve that one. So letter C. Which of the following expressions best represents the dot product of two vectors? Select all that apply. So which of these following expressions? Well, from our look before, right, what we just talked about on the page before this, we know it's going to be a magnitude A times magnitude B times the cosine of something. So it's going to be C or D. But in saying that, I notice that B is the same thing as C. So it is B and C. Okay, based on what we talked about here on this page, right? Walking through those formulas, it's going to be B and C. That doesn't really help us learn how to do these problems, so let's do another problem together. If the magnitude of U is 10 and the magnitude of V is 8, and the angle formed between them is 60 degrees, then what is U times V? So for this one, we're going to use that other formula, right? Where the magnitude of U times the magnitude of V times the cosine of theta is going to be our answer. So we have 10 times 8 times the cosine of 60 degrees. Let me grab my calculator here. So I have 80 times the cosine of 60, and the answer is 40. Okay. They didn't give us a unit of measure, so it's just going to be 40. All right, next page, 49. Let's do at least one of these together, but let's take a look. Find the dot product of the position vectors whose terminal points are at 8, 6 and 15, 8. All right, so for this one, we're going to take a sub x times b sub x plus a sub y times b sub y, okay? So we have 8 times 15 plus 6 times 8, okay? I don't know what 8 times 15 is, so we'll figure that out right quick. 120 plus 48 tells me this is 168, letter D. All right. There's only 2 left in this section. I don't want to do them all for you. So I'm going to leave those 2 for you to finish. And that is it for section 2 of Unit 6. As always, if you have any questions, don't hesitate to let me know. Otherwise, until next time.